In this lecture, I'm gonna talk about the situation when my system of equation is solvable. And by solvable, I mean I can always find a solution for the system of equations that I have, so that will always have a solution. Now, one condition that would guarantee that my system will always have a solution is when the rank of a matrix equal to the number of rows of my matrix, which is the value m. Now, if we look at the last example in the previous lecture, we see that the value m is the number of equations and the rank of the matrix is the number of equations that matters. So if these two numbers were to be equal, what that would mean is all equations that I have are actually gonna matter. So when these two things are equal, that means all equations matter. All equations matter. And why this is important? Because, well, if all equations matter, that means there will be no row equation. There will be no row equation. And by row equation, I mean things like 0 equal to 1. Yeah, because if all equations matter, then that means I'm not going to have something like this. That will mean that my system will not have a solution. So if we look at the example that we have down here, so I have a system, but let's kind of say that my a and b here, this is just some real number, but I don't know what these are. Now then, well, I can try to find the reduced row echelon form and the rank of my matrix A. Now then, this is not too hard. I can subtract the top row from the bottom row. I'm going to have 1, 1, and then 0, 1. I can now subtract the bottom row from the top row, so I'm going to have 1, 0, 0, 1. So the rank of this guy is going to be 2. The rank of this guy is going to be 2, and that is equal to the number of rows of my matrix, which is the number of equations that I have. So that means this two number is equal. I can always find a solution to this system. So this guy is always solvable. Always solvable. In other words, well, if I were to write down the equation for this, I'm going to have x plus y equal to a, and then x plus 2y equal to b. Even though I don't know what the values of a and b are, I can actually just subtract the top equation from the bottom one. So I'm going to have that y is just going to equal b minus a. I can substitute y here into the first equation, and that will give me the value of x, and that's going to be just 2a minus b. Yeah, so whatever the values of a and b are, I can always solve for x and y. So this one is always solvable. On the other hand, if I look at my part B, my matrix A is going to be 1, 1, 2, 2. And then I can just subtract, and I can just subtract 2 times row 1 from row 2. I'm going to have 1, 1, 0, 0. So this guy actually have rank 1. So we actually kind of did this earlier. It was in the example 1.6 part F. Although it's actually kind of easy enough to do by hand though. So the rank of my matrix is A, while my system has 2 rows earlier. So this is not the same. So this guy is not always solvable. And you can kind of see that it's actually solvable only when B is equal to 2A. So this guy is solvable only when B equal to 2A, and in which case there will be infinitely many solutions. If B is not equal to 2A though, this guy will have no solution. Now if I look at part C, we actually kind of did this earlier. It was in the example 1.5 part D, and also in 1.6 part E. However, what really happened here is that if I were to extract the matrix A that we have, I'm gonna have, let's see, the value is gonna be 1, 2, 1, 3, and then 3, 9, negative 3, and 1, and then 2, 5, 0, 7. We actually find the rank of this matrix earlier. That was in example 1.6 part F. And we see that the rank of this guy is 3. The rank of this guy is 3. The rank of my matrix A is going to be 3. And that is actually the same as the value m, which is the number of equations that I have. So I can actually guarantee that this guy is always solvable, even though I do not know what is the value that I have on the right hand side. So even if I want to solve part D, even if I do not know what is the value of A, B, and C are, this guy is always gonna be solvable. Always solvable. If I were to plug this into Wolfram, so let's kind of see what it will give me. So instead of 9, 0, and 20, let me actually just put in A, B, and C here, and let's see what Wolfram is gonna give me. Yeah, so like what we said earlier, this guy will always be solvable no matter what the values of A, B, and C are. My x1 is gonna be a free variable, and the value of x2, x3, and x4 is gonna depend on the value of x1 and the value of A, B, and C that we have on the right side here.